Welcome to the presentation on designing and simulating of a DC motor circuit for an assembly line with a horizontally moving conveyor belt. This project was made by Duaa AL Rahma, Mustafa Hassan, Nour Abdulrahman AL Busmait, and Ebrahim Altamimi. This presentation focuses on the design and simulation of a DC motor for a moving conveyor belt. The main objective is to maintain a constant speed of 200 RPM while accommodating varying load torques ranging from a minimum 3 Newton meters to a maximum of 24 Newton meters. Initially, manual control design is developed where the armature voltage is adjusted to a single-phase full-wave AC to DC converter. The design is then modified for an automatic control, allowing the circuit to be adjusted to the voltage automatically to maintain the desired speed. Simulation will be conducted using a suitable software such as MATLAB or Multisim to validate the design functionality. Regarding the design requirements, first, the motor type. To select a suitable DC motor capable of handling the load torque variations and maintaining a constant speed of 200 RPM. Second, the motor rating. To choose a motor sufficient power and torque ratings to meet the maximum load torque of 24 Newton meters. Third is the armature voltage adjustments. To design a single-phase, full-wave AC to DC converter to adjust to the armature voltage of the motor. Fourth is the input voltage and frequency. The converter should be compatible with an input voltage of 240 volts RMS and frequency of 50 Hz. Fifth is the constant speed. To ensure that the motor maintains a constant speed of 200 RPM under all loading conditions. Sixth is the simulation. To validate the design by simulating the circuit using a software such as MATLAB or Multisim. The DC motor values were first acquired by Simulink. Then, the same values were used to build up circuit on Multisim. The values can be shown on the right-hand side of the slide. These values were specifically chosen because they would die off with our requirements of this project.
After choosing the motor specifications from Simulink, I'm going to talk about how did we manage to calculate the parameters for the manual control. At first, we found the rated torque and the field current to find the armature field mutual inductance by using the omega formula, and we assumed the alpha to be 0, cosine of 0 equals to 1, therefore it won't affect on the original formula. Also, the value of the speed has been set based on the motor specification. After finding the K, we have to find the firing angle at minimum torque and maximum torque by using the omega formula, and the speed is set to 200 based on the desired speed. Therefore, we can know what is the minimum and the maximum firing angle for further use in Multisim.
Phase angle specifications. The phase angle controller works on controlling the pulse of the rectifier. Moreover, line frequency has been modified from 60 Hz to 50 Hz because the power supply generates 50 Hz. In regards to the pulse width and pulse amplitude, they were set by default. Testing the circuit and maximum torque. Single-phase AC voltage is 240 volts based on the requirements of the question. AC to DC converters using thyristor were controlled by the phase angle controller, which is further controlled by a variable DC voltage, utilizing the DC interactive voltage. In addition, one smoothing inductor was used to ensure current continuity, and the value of the inductor has been assumed by using trial and error methods. Furthermore, DC machine wound field. The values of the motors were set based on the values that were set on Simulink, and an arbitrary load has been connected to the output, and the core model type has been changed
to constant torque, and the torque has been set to 24 Newton meter, which is the desired maximum torque. Finally, the voltmeter has been connected to the output to test the speed.
This figure shows when the circuit is controlled manually. The value of the output speed has been measured when the load is set at minimum torque, which is 3 Newton meter, and the firing angle is set at the maximum value, which is 83.946, based on the calculations that were shown previously. And as can be seen, that we achieved the desired speed, which is 199.1. The small difference is because of the components tolerance and simulation errors, which is expected.
When it comes to the automatic control of the conveyor belt motor circuit, calculations had to be performed to obtain the values of A1, which is the control circuit gain, and V4, which is the DC power supply added to the control circuit. The calculations involved simultaneous equations utilizing the minimum and maximum alpha values calculated in the manual control design part, and the upper and lower output voltage limits preset by the PI controller in Multisim. The substitution method was used to calculate the values of the variables A1 and V4. The PI controller gains were set through trial and error to ensure minimal steady-state error and a smooth response. The trial and error method was used due to its simplicity and effectiveness. Additionally, the upper and lower output voltage limits used in the simultaneous equations in the previous slides can be observed in this window. The separately excited DC motor and the control circuit can be observed in this slide. The speed set point, which is 200 RPM or 20.94 radians per second, was introduced as a fixed voltage source connected to the input port of the PI controller. The positive output port was connected to the control circuit gain calculated earlier and into a summing junction, therefore summing it with the control circuit DC power supply, which was also obtained through the calculation earlier. The output of the summing junction feeds into the firing angle control block, hence controlling the thyristor's firing angle based on the load torque automatically. A simulation scenario showing the minimum specified load at 3 Newton meter is shown in the circuit in this slide. It can be observed that the speed of the motor was almost 200 RPM, therefore demonstrating the control system's accuracy.
This figure shows when the circuit is controlled automatically using PI controller. The value of the output speed has been measured when the load is set at random torque between the minimum and the maximum value, which is 14 Newton meter. And as can be seen that we achieved the desired speed, which is 199.73 RPM, and it is approximately 200 RPM.
And as seen in this figure, the system using the PI controller successfully achieved the required speed, that is approximately 200 RPM, at the maximum torque, that is 24 Newton meter. For the next slide, that is figuring out the percentage error for the automatic operation, where we ended up with an error of 250 micropercent for the minimum torque and 50 milli for the maximum torque, where both can be considered negligible and they occurred as a result of what component tolerance and simulations error. To sum up this project, the goal was to design and implement manual and automatic speed control circuits for a DC separately excited motor by maintaining the speed a constant at 200 RPM in two different torques, the 3 and the 24 Newton meter, where we concluded in the manual speed control design that in order to maintain the speed 200 RPM is by changing the load torque and the firing angle manually. And on the other hand, for the automatic speed control operation, the designed PI controller would control and fix the firing angle as per as the applied torque from the load. And thank you.